Welcome back, everybody, and to a new session on machine learning. Now, the topic today is going to be a little bit more, how to say, not very interactive, in the sense that we are going to present material about convolutional neural networks. So why do we care about this topic? Now, till now, we have been working on deep learning methods and neural networks. Now, neural networks are what we call, in essence, mathematically for affine transformations. So that means that we keep a full matrix, which could contain our input data. We multiply that with a weight matrix, and then we propagate these results till the endpoint. And then we go back and forth with updates of the gradients and the parameters until we have reached an accuracy or a mean squared error or whatever kind of cost function we are evaluating to a given precision. So if you're dealing with a mean squared error, this often means us having it as close to zero as possible. Now, when we come to large images, if you're dealing with an image of, let's say, 200 times 200 pixels, this is going to give us 40,000 input nodes for just one image. And then you would like to train this on millions of images. And if you now look back to the exercises you did last week and the week before, you know quickly that the dimensionality of a typical problem with a neural network is going to give you a code which will run very, very slowly. So we need to find ways to reduce the dimensionality. And this is where convolutional neural networks come in. And convolutional neural networks, you can read them or think of them as ways to reduce the dimensionality of the problem, and where you focus on specific features. So they are based on the mathematics of convolution, which, if you're familiar with convolution, if you have dealt with image analysis or time series analysis, you may have heard about filters, Fourier transforms, and topics like that. So the filters are ways to reduce the dimensionality of a given image, for instance. So convolutional neural networks are extremely popular when it comes to images and recognizing images. And this is one of the fields which you can say really kicked off these kind of deep learning methods. So image recognition is actually one of the perhaps most successful applications of deep learning methods. And if you think of perhaps one of the most important ones when it comes to, let's say, medical analysis of scans of patients, this is actually where convolutional neural networks play a really important role in applications of them. So this is going to be the topic today and also partly next week. Now, in this case, writing your own code, like we have been doing in project number 2 here, is going to take too much time. This is a semester project. So if you're taking the advanced course on machine learning, we have one which runs in this fall semester. We also have a course at the Departments of Computer Science, which is called Machine Learning for Imaging. There you would typically dive into the development of a code for convolutional neural networks. But at the heart of many of these methods, you will find a classical neural network code. So a convolutional neural network is actually you reducing the dimensionality till you can treat the data with a standard feed-forward neural network. So inside a convolutional neural network, there is a feed-forward neural network. So we are going to, when it comes to project number 3, where actually quite many apply convolutional neural networks to the, let's say, image classification types of problems, then what we normally recommend is to use either TensorFlow, which many actually do, and we will show you examples on how you can use TensorFlow for imaging with convolutional neural networks. And then the important thing for you is actually to understand what a convolutional neural network is doing mathematically. And this is more the topic of today, together with examples on how you can use TensorFlow to perform an image recognition. So when it comes to the other material here, so you have a link to the textbook of Rashka, and in chapter 14, there is actually an alternative to TensorFlow where you use PyTorch. So feel free to look up the Jupyter Notebook from the textbook of Rashka et al., because that contains similar examples. And if you want to do this in project number 3, because then you're much freer to choose the topic you want to look at, feel free to use these code examples, either from the lecture notes here or from the textbook of Rashka, if you prefer to use PyTorch. So this is these are things, background things, which are important to think of. And when it comes to the lab sessions tomorrow and on Wednesday, we are going to focus only on project number 2. However, if you did not finish the exercises from last week, feel free to keep working on them, and you can hand them in this coming Friday as well. So if you didn't finish it, if you had some small problems, some of you had, we will keep working on them. But then the main focus is on project number 2. Also, and you probably have seen that in the weekly email, we are going to send you feedback on project 1 by the end of the day today or early tomorrow. The grade or the score is something which we will add a little bit later, but you will get the main feedback about what you did in project 1 in case there were some kind of small things which you forgot, etc., etc. So the main feedback is going to be uploaded on Canvas. And then gradually, because we have to be 2 on each project, 2 grades, and then we are actually going through all the scores in common, which means that we have to have a kind of equal and fair measure for everybody. So normally we put the scores during the week. But the important thing is actually the feedback on project number 1. Any questions so far? So, as I said, today, the lecture is going to be a little bit more passive in the sense that I will more preach here, and then we will have less of the kind of more interactive involvement. And one of the reasons for that is that I wanted to focus a little bit on the mathematics of convolutional neural networks and how you can implement them. In the slides for this week, you will also find an example of how to write an own code for convolutional neural networks. But this is well beyond the topic for this course, because that is, as I said, close to a 1-semester project. Okay, so if we look at this convolutional neural network stuff, one of the main differences is that we, when compared with standard neural networks, is that now we are going to have an intermediate step. And that intermediate step is provided by the mathematics of convolution, which you can think of as a filter on your data, where you reduce the dimensionality. And one of the reasons for that is that if you take an image of a house could be an image of 200 times 200 pixels, as I mentioned, which would means that you would have 40,000 input nodes. But if you think of the house, I mean, the walls of the house are not that very interesting to keep track of what kind of color they have. What you would be more interested in, if you prepare a filter for recognizing houses, is where the corners are, where the windows are, where the roof is, etc. Things which typically are representative for a house. What often also happens is that some of the pixels which are close to each other may be more interesting than those which are apart from each other. So if you think of pixels representing the color of the wall, they would be spread out uniformly, and that's not so interesting to keep track of. So you would be more interested in keeping track of those pixels which tell you where a window is located, and where the roof is located, and where the corners are. So that's a typical example of how you would filter out information. So the neural networks, as we defined, they are normally called affine transformations. So mathematically, this is what you have been doing in project number 2. So you take your input vector or input matrix, your design matrix, and then you multiply that with another matrix which represents the weights. And you just transform your data by multiplying with the weights, adding a bias vector, you produce an output, and then you propagate this. But you keep all the information, so the matrices are dense. You are not reducing the dimensionalities of these matrices. And these are normally called affine transformations. Whereas CNNs actually, if you now look at the sound clips or images and so ever, they have some intrinsic structure. So when you're dealing with CNNs, in a certain sense, this becomes a kind of art, because you have to be knowledgeable about the data which you're representing. That means that you need to have some kind of intrinsic knowledge about the inner structure, and you want to understand what are the basic things you want to take care of. So there could be, if you now think of some important properties of images, they are typically stored as multidimensional arrays, like the pixels of a figure. They feature one or more axes. So that could be the width and the height axis for an image. It could be the time axis for a sound clip. And one axis, which is called a channel axis, is used to access different views of the data. So when you're dealing with images, you would normally have the pixels in 2 dimensions, but then you would also have the colors, which are represented by 3 channels, red, green, and blue. So that means that if you have 200 pixels, the image would be of a tensor of dimensionality 200 times 3 for the 3 color channels. So you see quickly that that dimensionality becomes huge. And what I have here are some simple examples. If you think of, as I said, an image like the MNIST data, which we looked at earlier, if you have 32 times 32 times 3 color channels, that means that if you link that with a fully connected neural network, a hidden layer, then you would have 32 times 32 times 3 weight parameters, which you would need to think of. And if you do a larger image, it would quickly enter into something like 120,000 if you have 200 times 200 times 3 color channels. So what we are looking after is a way to reduce the dimensionality. The way this works is schematically seen here. So if you think of this as your input, so it could be the depth here could represent the color channels, and the width and the height could then be the number of pixels. Then this is reduced by some kind of filter. It can be further reduced, and then it's sent in this box here, which is a standard convolutional neural net, no, a standard feed-forward neural network, where you do the final training. So the filtering here is what plays an essential role, and that means that you have to think of different filters for different types of problems. So a convolutional neural network is something which is often more tailor-made to specific problems, where you are the one who has to think of what kind of properties do you want to encode in the filter. Now, you do have huge trained neural networks which have been trained on tons of images. And we have data sets where you have actually pre-trained convolutional neural networks, which you could use in a more general purpose. So these are networks which have been trained on buildings, on trees, on flowers, on animals, humans, etc., etc. So that means that some of these data sets are really huge, and the networks are very deep, and they are time-consuming to train. So there are many such pre-trained networks which many people use as input to other types of problems, where you don't need to think of training specific filters for a specific problem. So I don't know how familiar you are with the process of convolution and filters in imaging, but this is a pretty common recipe by which you can then try to reduce the dimensionality of the information which you have. So there is an example here. So if you have in a field like signal processing, or this applies to imaging as well, you design, as I said, so-called filters, and these filters are defined by the convolutions and are often handcrafted. And one may specify filter for smoothing, edge detection, frequency reshaping, and many more other types of operations. And if you now think of your input vector as a vector of dimensionality 10 to the 6th, then you could set up a neural network with only one hidden layer, which has 10,000 nodes. And that means that you would have 10 to the 10th weights, plus some 10 to the 4th biases. And if you then have 10 to the 4th output nodes, then you get with something like 10 to the 4th weights for the output node. And if you have only one type of not just one output node, but which connects to the 10,000 hidden nodes, then you get of the order of 10,000 to the 10th plus the bias in the hidden layer, plus the weights in the output, which link to just one output node plus one bias. So this is roughly 10 to the 10th. So this number of parameters are pretty huge. So when we now come to this setup of a convolutional neural network, there is some kind of naming. And this introduces an architecture, which is our model. And you will see how we do that with TensorFlow. And there are some parameters. And some of these parameters are fixed. So you have your input, which is the same as before. This is the input layer. And if you're thinking of images, this could be 32 times 32 pixels times 3, which are the color channels. Then there is a convolutional layer where we reduce the dimensionality. But normally this dimensionality is not dramatically reduced in the first convolutional layer. So what often happens is that you make a small reduction and you make replicas of the images. So you could actually make 10 new images, but with a smaller number of pixels each. And they represent then different features of your original image. And this is the convolutional layers. So in this case, what we take, we keep the 32 times 32 pixels, and we actually increase the dimensionality here, which is normally not the case. Normally you would have a smaller image. And then there is a so-called ReLU layer where you apply an element-wise activation function. And this leaves the volume unchanged. So this ReLU layer is fixed from the beginning. So you don't change the parameter of that specific activation function. Now, the weights you will have in the filters, they are being trained by backpropagation. So in the convolution stage, you will have new parameters which are being trained. And I'm going to set up examples throughout the lecture here on how many parameters you end up with when you perform this and this type of filtering. But there are parts here where you have hyperparameters which are set from the beginning and you don't change. Then there is something which is called a pooling layer. This is a downsampling where you reduce the dimensionality further. So what you could do then is that you could take an image which is represented as a matrix, let's say 32 times 32 pixels, and you split this in sub-matrices of blocks of 4 times 4. You have performed a ReLU calculation where you find a specific value for each of these elements of that matrix. But then, since you have split it down, a matrix which is 32 times 32 in smaller blocks of 2 by 2 matrices, from each 2x2 matrix, you pick only the largest value. So that means that you keep only that one, and this is called max pooling. So you pull out the max value of a submatrix. And that's the one which you keep propagating. Now then, what you can do, if you look at this stage here, convolutional, ReLU, and pooling, you can then repeat this. You can make this network deeper and deeper. And that means that you have further filtering of your image. And at a certain point, you say, stop. So in this specific case, we have only one so-called convolutional setup with convolutional, ReLU, and pooling. And this is then flattened and sent in to a fully connected neural network, where you do the training with backpropagation as you did before. So the stages are as follows. You take an image, you have some filter, and you scale it down. This is the convolutional stage, where you have three types of operation: mathematical convolution, and then you have this ReLU operation, where you spit out an output, as you did in the neural network case. And then you pick the largest values, which are given by this pooling, or sometimes you can keep the average value of some slots. And then this is what is sent in to a standard feed-forward neural network. So at the heart of your convolutional neural network, there is a standard neural network running. And you will see that many of these methods, like next week when we discuss recurrent neural networks, you will also see that typically at the heart, there is going to be a neural network, which you have written now in project number 2, or are at the end of the setting up. The same applies if you're dealing with autoencoders, which is not the topic for this course, but in more advanced topics, and many more advanced methods. So a neural network, that part is essential because it serves as a kind of elementary block in many of these more advanced methods. Yeah. No, so you would go through the whole process, and then you do the backpropagation feed. You do the backpropagation on the neural network, and then you go back to the convolutional stage, and then back and forth again. So if we now look at this CNN in brief, a CNN architecture is the simplest case, a list of layers that transform the image volume into an output volume. So as I said, there you have this convolutional ReLU pool, and then the standard neural networks. These are the most popular ones. And what you would typically see then is that you have some filter, which is a 5x5 filter here. And this actually produces 32 copies of this. This is an image which has 28 times 28 pixels, and it has just one color channel. And then you have different stages here where you do one convolution, you do a new convolution, and at the end, this is sent into a standard feed-forward neural network, and then you have a final output. So if these are this could be the MNIST data, where you see that you have 10 output nodes, and the 10 output nodes will represent then the 10 handwritten numbers. So you can do many convolutionals and pooling stages, and then you have reduced the dimensionality. You can produce many more images, but they are often of reduced dimensionality, and then that is flattened out as a long vector and sent into a standard feed-forward neural network, which is this FC part you see at the end. So the key idea is actually to have a dense neural network, which is represented by an affine operation like matrix-matrix multiplications, and the key, which is a standard neural network. And the key idea of CNNs is that in images, neighbor pixels tend to be related. So we connect only neighboring neurons in the input instead of connecting all with the first hidden layer. So one thing which I wanted to say, however, is what did we actually do before when we compressed an image? How did we actually store a compressed image? And one of the ways by which this was done is by singular value decomposition. This was, I mean, till convolutional neural networks came on the market, besides filtering with different types of filters, was actually to perform a singular value decomposition. Remember now that the singular value decomposition, you would start with a given matrix. So if this is an image with, let's say, 200 times 200 pixels, then by a singular value decomposition, you could now keep only some of the singular vectors. So that means that you make a projection. So if you have a 200 times 200 as a dimensionality, you would get 40,000 eigenvalues or singular values and 40,000 singular vectors. That information is your singular value decomposition of that specific matrix. You represent now an image as a matrix, 200 times 200 pixels. And then you perform a singular value decomposition on that. And every vector then can then be used to reduce the dimensionality. You can keep only 5 vectors, those which have the largest singular values, or you can keep increasing it. Now, the problem here is that if you want to reconstruct the whole image, you need to take care of all the vectors. But you can represent then just the image with just some few singular vectors. So let's see how we can do that. So there's a simple example program here where we actually take an image and we reduce its dimensionality here by simply taking a large image and then looking at different splits. So this is an image of if you haven't been to this place, this is a place you should visit. It's a beautiful town in Tuscany. It's called Volterra. And it's a town with more than 3,000 years of history. It was settled by the Etruscans, and then it became a Roman city. And it's a kind of Florence in miniature. And it's on a hilltop, 600 meters above the sea level. And it has a fantastic view. And it's a beautiful place. But here you can see now, if I now do the blurring. So here I keep only 5 of the singular vectors. So this could be one way to represent this image, but now you don't see much. And in this case here, the compression rate. So I have only 1% of the information kept. And there's quite some mean square deviation from the original image. And the original size of the image was actually 96,000, no, 600,000. I can start to increase and keep now 10 of the singular vectors. And then I can keep increasing this. And you see now with 20, I'm getting something which looks recognizable. And with 100 here, which is this specific case, and that should have, so this is this has a compression rate of 20%. And you see now that you can actually read what's written on the walls here. And this is a typical example on how you would compress an image and use that blurred image as the thing you would store. But if you want to reconstruct the whole image, then you clearly need to take care of all the singular vectors. But if this is okay enough, then this is the image you would store, if that conveys most of the information you're interested in. And this was the standard way by which we before would typically store information about images. Okay? So that's where the singular value decomposition comes in. And that was a pretty common and standard technique for image processing and reductions of the dimensionalities. And you can see here when we get to k equal 200, that is a case, so I think it was 400 here. Let me just see with 400. I have let me see now, with 200 here, I have a compression rate of 42% roughly. Okay, so this was just a small demonstration. So what I wanted to say now before we switch over to the whiteboard is to say a little bit about the mathematics of convolution and how this is implemented. Because at the end, even if this sounds a little bit unfamiliar to many of you, at the very end, what we end up with are matrix multiplications again, but these matrices of a smaller dimensionality. So mathematically, we end up with much of the same operations as we did with the standard feed-forward neural networks, except that now we are using the mathematical process of convolution. And what that means is something you can think of in a simple term. If you look at this first integral here, the way you can think of that, if you look at this integral here, is that you are making some measurements of, let's say, the position of an object. So this is this x of a, and this x of a can contain a lot of noise, which you want to get rid of. Now, what you have then is that you multiply this noise with some function w, which is often called the weight function or just a filter. So that means that at the time t minus a there, that is when you start filtering out all the noisy data which you have. So suppose now you make a measurement from a variable a to t. And a lot of the data before this t is pretty noisy. So what you're doing now is that you're filtering out, or you're weighting data which are less noisy by this function w, which we haven't defined here. This equation which you see there is the mathematical operation of convolution. And mathematically, we often write it like this: x times w as a function of t. And if we're having this as a discretized version, which is the most common case which we encounter, this is now simply replaced by a going from minus infinity to plus infinity. And then it's x, our input variable, is multiplied with some filters, some weights, and we have a final output. So in order to gain some intuition here, we are going to look at an example. And this example contains a lot of these tricks, which we are also going to implement when we write a code for convolutional neural network. So I promised you that there are going to be new hyperparameters. And these hyperparameters are parameters you set when you define the architecture and the model. And these hyperparameters have some funny names. One is called padding, which we are going to see as a mathematical tool for performing efficient matrix multiplications, and in order to represent the data better. And there is another parameter which is going to be called stride. So for those of you with Lord of the Rings, it's not Strider, but it's stride. So this was just a Lord of the Rings joke from my side, if you're familiar with those movies. So we are going to encounter two new parameters, but in order to understand that, we are going to look at a specific example here. And I'm going to slow down a little bit by switching over to the whiteboard pretty soon. So what we are going to look at, and hopefully this gives you the basics and how some of these hyperparameters come in the game here. So we're going to look at the polynomial multiplication, and we can write this in a compact way as a matrix vector matrix multiplication. And that gives us some of the basic foundation for understanding how a convolutional neural network is encoded. So if we look at that example, what we have is a polynomial of degree 2 and a polynomial of degree 3, which we want to multiply with each other. So what we know then is that when we perform this multiplication, we are going to get a polynomial of, obviously, of degree 5, because we have a polynomial of degree 3 and a polynomial of degree 2. So I hope you don't get offended if I go through in this kind of pedantic way. But if you then look at the multiplications here, when you look at the parameters you're setting up, these deltas, they are now given by these combinations from the polynomial P and the polynomial S, So the parameter delta 0 is simply A0, beta 0. Delta 1 is the first order term, which we have here. Delta 2 is the second order term, and that contains these different combinations here. So this is not very exciting. And we can write this in a general way without thinking. And the way we can do that is simply to, even if we note that the alpha I is 0, except for 3 cases, and beta I is 0, except for 4 cases, because this is a third order polynomial, the last one, we can write this delta J in this way, as you see here. So what we have done is to write a polynomial multiplication in terms of the mathematics of convolution. So what you see there is nothing but us implementing the mathematics of convolution. So this expression, if you look at these terms you have here, can then be obtained by simply putting up in a slavish way, I goes from infinity up to infinity, from I goes to minus infinity. Any questions so far? Now, this is obviously not a very intelligent way of doing that. So we are going to rewrite this formula in a more compact way. And that means that we may have the problem with some of the elements of a vector which are not defined properly. And that not having defined elements properly is going to lead to a hyperparameter which is called the padding parameter. Like everything in efficient matrix or matrix vector multiplications. So we'll just keep this formula here. So this is essentially just a way of writing the polynomial multiplication. Or you could write like that. But now what we could do is to write it in this way here, as you see. So we could then start with k equals 0 and perform a summation. And m is 3 in our case. And the maximum, which is the maximum length of the vector alpha. And beta has length 4 because it's a third order polynomial. And one way to do this is actually to write it in this way. So we can write it as a matrix times a vector beta. That's another way of setting up this polynomial multiplication. Now, a convolutional process is what we mathematically call for commutative. And you can actually see, and it's not so difficult to see that you can have this one written in terms of a matrix with the betas multiplied with a vector A0. Actually, the second one is better from a computational point of view because it involves less floating point operations. And these matrices which you see here, they have a name in the literature. So when we are doing this kind of convolution with the data we have, we are going to translate everything in terms of matrix vector or matrix computations, where these matrices are called Toeplitz matrices. So this is one of the basic mathematical ways which we are going to utilize in the process of setting up a convolutional neural network. So this is what lies behind the mathematics for a convolutional neural network. So if you look at this example, then this is this example conveys the basic mathematics. And later, when we look at the codes, our own codes, you will see that this is the kind of approach which we are going to implement. There's a lot of discussion here. There's actually something which is called Fourier filters for convolutional neural networks. And this is a very active research field here. But what I want to do now is actually to generalize a little bit this example which we have. And in order to do that, because we want to introduce this parameter, which is called padding, and I also want to describe to you what this stride parameter actually means. So these are two hyperparameters which are used in the setup of a filter. So let's switch here to the whiteboard. And please, if you have any questions, I hope this example here is transparent enough that you see the basic mathematics of a convolutional process. So this example with a polynomial multiplication conveys the essence of the process of convolution, the way it's used in setting up different filters. And we will come back a little bit later to how we would represent some input data of an image and how we could set up specific filters later. But let's continue a little bit with this simple example here. So what I'm going to do now, before I switch to the whiteboard, I'm going to replace these polynomial parameters beta and alpha with x and y's, and the parameters which I had, which I previously called for a parameter delta, is now going to simply be the y here. And this is the expression which I'm going to look at. So I have a w here, which is going to play the role of a filter. So in our simple case with a polynomial of degree 2 multiplied with a polynomial of degree 4, then this polynomial of degree 2 multiplied with a polynomial of degree 3, giving at most a polynomial of degree 5, then this m value is equal to 3, which is the number of parameters we have for a polynomial of degree 2. So we will assume, and this is pretty common, is that this filter has a smaller dimensionality than your input value x. So x can now represent your image, which you're feeding in to a network. And that could be a large matrix. In our case here, this is just a vector. So let's switch over to the whiteboard and see how we can manipulate this expression, which you see here, and rewrite this in a compact vector times a vector multiplication. And then we generalize it to a matrix times a matrix, where the matrix now represents your input data, and the other matrix represents the filter we are going to apply. So let's now switch again. So hopefully now you can see this example here. So what we are going to look at, since we now made this change, we have a function which I call y of I, and I write it like this. And this is now given by a sum over k equals 0 up to k equal m minus 1. And the original formula which we put up was simply given by let me just now find my notes here so I don't mess it up. So we have an x of a function of I minus k times a w of k. And since we had a second order polynomial multiplied with a third order polynomial, so that means that the dimensionality of this one is larger. So this is our input. This is normally called a weight or a filter / filter. And in our particular case, we had m equal to 3. So when we then set up the different operations here, and we looked at y of 0, this is now given by some x of 0 times w of 0. But then you see that I'm running into some problems. I have a minus 1, and I have a w1 plus an x of minus 2 of w2. Now, in my case, the only parameters which I had, so originally, what I have is x0, and then I have x1, and x of 2, and x of 3. And then I had so this is the third order polynomial, third order. And we actually label that as a beta 0, a beta 1, a beta 2, and then we had a beta 3. And then we had the other polynomial, which now had variables W0, W1, and W2. And that was the second order polynomial. And in our original example, we called this alpha 0, alpha 1, and alpha 2. So if you now were to store a vector representing the parameters in front of the x's in a polynomial, then we see now that we are calling, when we are implementing this function, we're actually trying to access elements which don't exist. So suppose now that you have stored a vector of length 4 here. You have x0, x1, x2, but now we have elements which are not there. So how do we cope with that problem? And you see that this problem here appears also in the next case. If I now look at this y of 1, I will have an x0, which we have, w0, and I'm going to have a an x w1 times an x0, but then I'm going to have an x minus 1 of w2. And this guy here is also not defined in the original vector. Furthermore, what you will see now, if we move down, before we take a small break here, if we move down to y of 5, you will have a variable x of 5 multiplied with w0, which we have defined, plus an x of 4, which we do have, of w1, plus a w2 here, multiplied with an x of 3. So in this particular case, this x of 5 is something which we have not defined. And furthermore, if we now look back here to this example which we put up here, we have x0 up to x3. So that means that this x4 is also not defined. So let's ring them in here. So what we have are parameters x5, x4, and x minus 1 and x minus 2, which are not defined here. So one thing we can do now is simply just to increase the size of that vector. So if you now think of the different boxes which we put in for x, because w, the sum runs over all the values properly defined for w. So we have a slot in memory with x0, we have x1, and we have x2, and then we have x3. These are the coefficients for polynomial of degree 3. But what we could do now is simply to increase this dimensionality here so that we have an x of 4, and then we have an x of 5, and then we could now simply add to the end here an x minus 2 and an x minus 1. So what are we doing here? We're actually putting a padding at the endpoints. And this leads to a parameter, a padding parameter, which has value 2. So we add 2 values at each endpoint. So this is just a way which we are going to use now to perform the vector-vector multiplication in a more efficient way. It has also some other important features which we will see after the break. But now we are going to stop here and take a small break.
Two vectors being multiplied with each other. So these operations reflect some of the basic philosophy which we have when we do a set up a convolutional neural network. So you can think of this W as a kind of filter which normally has a smaller dimensionality than the input variable x, which we give him. So in this case, we are just dealing with a very simple case, which is defined by this polynomial multiplication. So what we can do now
to rewrite and redefine the variables x minus 2, x minus 1. So we could simply rewrite this to x0, x1, etc. So there's nothing which hinders us from redefining the summation variables. So instead of having a function which is defined as the one you see here, where we simply sum up to k equal m minus 1, which is the degree of the lowest polynomial in this case. And we have a sum over, or x is defined by I minus k. Then we could now simply redefine this. But one thing which I wanted to say a little bit about first is that if we now look at these additional values which we have added here, these two and these two, which are not defined in principle by the polynomial, this is normally called padding, what you see here. And that introduces a parameter. So that parameter becomes a hyperparameter, which is normally fixed when we run the calculations. And then you could tune it by changing the calculation. So this is a hyperparameter P for padding. So that means that for this specific case, what we had is a so-called a padded vector where we now have added two elements to each side. And with size, and we have a size n, which is the original size. And we had a polynomial of degree 3, the largest polynomial. And that had 4 elements. So n was equal to 4 plus 2 times p. And this p is in this case equal to 2. So this is the formula which we normally add. So 2, because we add 1 to each end. But in this case, we add 2 numbers. So in this case, this is equal to 4 plus 4, and that's obviously equal to 8, if I've done the mathematics correctly. And you see that here now, because we have added, or we get actually in the expressions, we get terms when we use in a slavish manner this formula here. Then you see now that we have an x minus 2 and x minus 1 to the left. And then we get to the final one, the final point. We have an x5 and an x4 here, which were also not in the original set. So what we do next now is simply to rewrite. So we relabel or reorder this array. So we define now x0, so redefine, and we keep the same label. We set that to x minus 2, and that means that we put x1 is equal to this x minus 1, and that means that x2 is actually the original x0, and this continues all the way up to the final one. Then we can rewrite the formula which we had. This y of I here is now going to be given by the following expression up to k equal m minus 1. So m is the dimension of the smallest vector, which was the lowest polynomial in this case. And we would simply rewrite this as an x of I, and we have plus, and I have an m minus 1 minus k multiplied with this w of k. So this is the way we would simply rewrite that summation when we have performed this type of so-called padding here. And then you would see now that when we perform the sums, you would get a y0 term, which is simply given by x2 times w0. And originally, that was given when we go back to the original expression for the polynomial in terms of alpha 0 and beta 0. That was the original equation which we started with. And then we switched to the x and w's to stay more in line with the standard way of thinking of convolutional expressions. And then we get a new term, which is a y1 here, which is then given by x4 times w0 plus x3 times w1 plus an x2 multiplied with a w2 here. Now, if you look at these expressions here, there is an even better way of setting this up. So what we could do now is to rewrite these w's. So I could now redefine it, because what I could do is to, if we look at the first expression which we have here, this one, which is simpler to read, we could now redefine a new vector where this w0 is now given by a w tilde 2. So this is just a redefinition of the vectors. So if we do that, what happens is that we can write, if we redefine, so I define a w2 here, which is the same as the original w0. I have a w tilde 1, which is actually the original 1 here. And then I have a w20, which is w2 here. If I do that, then I can rewrite, right, the multiplication or the setup of this convolutional product, the whole operation as a vector x, which now takes values from I plus m, like this. So we take out that specific part. So this is just a vector which starts with index I, and then goes from I plus m, and m is the length of this vector w. And I can simply multiply that, look at that as a dot product of these two vectors. So that is a considerable simplification of that operation. But we have introduced something which we have called for padding. Now, what I want to do now is to go back to the slides. So let's just do that. And let me find, just need to. You just bring up that one. Okay. There we are. So if we now look at what we said now, what you will find in the slides here is just a repetition of what we did. So as you saw, if we just take this expression here, that leaves us with some terms with negative indices, which may not be defined. And padding then came into play, and we added two values to the left and two values to the right. And this is one of the quantities which is introduced and then normally gives an additional parameter to the setup of the hyperparameters. So in our case, the length of x, which originally was equal to 4, is now increased to length of 8. And this parameter p is equal to 2. So that plays the role of a new hyperparameter. So what we ended up with then is a new vector which runs like this. So originally this was set to 0. So when we rewrote them, because we start with the index 0, and then x2 is the same as the original beta 0, etc., etc. And then we end up with x7 here. And then we can rewrite this term like that. So what you see now, if you take a y equal to 4, you will get these terms. And one of these is 0, as before. And these were the terms which we had for a fourth-order component in the polynomial, a third-order component in the polynomial. And this x6 times w0 is actually 0. And in a similar way, you can set up all the other parameters and recover what you had originally. So this is just a kind of rewrite of the original vector, two vectors representing a polynomial multiplication. But then we can rewrite it as dot products, because if you see now this y0 here, which is given by these three terms, I can now simply relabel w0 with a w tilde 2. And that means that I can rewrite everything as a dot product of x starting with y plus m minus 1 multiplied with a vector w. So one thing which we also are going to look at now is the case of a two-dimensional object, because that is going to say a little bit more about what this padding means and why it is important. So the kind of argument which I gave you now was a technical one, where we simply added two elements to each side in order to set up an efficient vector-vector multiplication. So this is something which is often vectorized when we do the operations, and it's easy to implement and it's efficient to implement and to perform the operations with. So when we have a two-dimensional object, again, we would write this. So this could be the input x, and this would be this filter, this weight. And then we would typically write this in terms of a summation of m and n. But since it's a commutative process convolution, you can rewrite it in terms of I minus n for x. And normally this is better to do because the dimensionalities of w's are normally smaller than the dimensionality of x. So if you go back to what we discussed before the break, so let me just go back again. If you look at the way we wrote the polynomial multiplication in terms of a matrix, a so-called Toeplitz matrix, we could write it out as a 6 times 4 matrix times a vector of length 4, or we can write it out as a matrix of length 8 times 3 multiplied with a vector of length 3. And this is from a computational point of view, is normally a preferred way of doing that, because the filter has normally a lower dimensionality than the input. So the two-dimensional object is often rewritten in terms of this operation which you see here. But sometimes most deep learning libraries actually implement this convolution in terms of something which they call cross-correlation. And this will be written like this. Now, if you now look at this example here, you could now think of you having an input image, which is given by a 3 by 3 matrix. Then we apply a filter to this image. And this filter has now a dimensionality of 2 times 2. So if you now look at the way the multiplication is done, this introduces another parameter in the calculations. So think of this subblock, the first 2 by 2 subblock, which you have here. So you have an x00, x01, x10, and x11. Then what we can do now is that we can multiply this subblock. This 2 by 2 subblock is multiplied by this 2 by 2 matrix. And if you perform the multiplication, this is what you get. This is actually the application of convolution here. Now, so the first element of this new matrix is given by us multiplying the 2 by 2 matrix you see here with a filter. So that just gives us a number, which is now given by this first line here. The next thing I do now is to move one step. So moving one step only, so that means I move one column. That gives me a new hyperparameter, which is called stride. So in this case, stride is equal to 1. So that means that my next thing is that I take this 2 by 2 matrix, which is given by this one. And for this particular case, I cannot have a stride equal to 2, because if I were to jump over this column and place myself here, I would only have 2 elements, and I could not multiply a 2 by 1 matrix with a 2 by 2 matrix. That's not possible, right? So in this specific case, I can only go one column at a time. So I take these 2 guys here, and then I move in here. So let's go back to the whiteboard and set up this example here, so that you get it correctly. So let's just put this up. So if you look at this example which we had, where we have a matrix now which has an element x00, x01, x02, and then I have an x10, x20. And then I'm performing the convolution with a filter with only 4 elements. So this is a 2 by 2 filter. So this is a 3 by 3, that's the input. And this is a 2 by 2 filter. Now, if you look at this operation, which we are going to do now, the first step we do is actually to multiply this one with the filter. So that gives us, in this specific case, we have x00 times w00 plus x01 times w01 plus x10 times w01 plus x11 times w11. Our next case is now taking the next step. So we just move with one column. So now we have a new submatrix, which is again a 2 by 2 matrix, and that would fill in the black dots here. Then we could now bring in a new matrix here. So let's now take this multiplication, this one, and that would give us the blue dots here. And then finally, we would take this matrix here, and that would give us the red dots when we perform the calculations. In this case, what we have done is that we have moved one column at a time. So that means that there is a new parameter, which is called stride. And this is S, and it's called, and it has a value equal to 1 here. So if I put stride equal to 2 on the other hand, what would happen then is that I would only have these 2 elements, which would have to be convoluted with the 2 by 2 matrix. And that is not possible, because what I would get then is a 2 by 1 multiplied with a 2 by 2. And that is not a possible operation. So that means for this specific case, I can only move by stride equal to 1. So I go this way, and then I take the next subblock like that, and then the next subblock. So stride becomes a hyperparameter, which you, on the same footing as this padding, would fix in the beginning of the architecture. Then how you jump, how fast you jump in this matrix X, which you're multiplying, you're convoluting with matrix W. This is something one can play around with. And it depends also on how many pixels, if this is an image, you want to link. Now, there is another thing concerning padding, which I want to bring back here. So let's bring back the Jupyter notebook. So if you look at the case which we had here, the only possibility is a stride equal to 1. And this is the result we get when we have performed the convolution. Now, if you notice one thing, and you go back to the matrix you have in your notes, the matrix X, what you will see now is that the endpoints, they appear only at one place. So X00 appears only here, but middle points like this X11 comes here, it appears here, it appears here as well, as you can see, and it also appears here. So this is a case where we only had a 3x3 matrix. If you make a larger matrix, what you will see very clearly then is that the endpoints will only appear in one specific place in this output matrix. So what is common to do then is to make this padding around the matrix. And when you do this padding, so you just add zeros outside the matrix, then when you perform the convolution, then these endpoints will appear in many more places. So padding becomes a variable, which then, if you look beside that simple polynomial multiplication, which we looked at, this becomes a way by which pixels represented by the x's appears in more than one output element. So this X11 is, if you look back at the matrix, is the element in the middle. So when we now perform these multiplications, if you now look back here, you see that X11 is here, whereas all the other ones are just endpoints or points on the border. So if you then increase the size of the matrix and you just put zeros around it, and then you reperform the multiplication or the convolution, which is more correctly, then you get a new output which contains also the endpoints in several places. So this is a way to avoid that some of the information is just kept in one place and plays a less important role than other points. Because you see now for this specific case, if we don't do any padding, this X11 appears in all the places here. So that information is carried with us in more than just one place. So one way this is often rewritten is actually to rewrite or to flatten out a new vector, which we call x prime of length n, which now contains the matrix. And instead of performing the convolution like we did here, we just write this by defining a new matrix as a matrix vector multiplication. And this is the way which you normally would implement the filter. So in convolution. So this is totally equivalent to just setting up the convolution, which you would then rewrite as a matrix vector or a matrix multiplication. And this is normally the way it is implemented in basically all codes here. So when you're setting up this kind of convolution stage, if we now look at the different approaches which we have, so we are going to jump back to the whiteboard and set up this more slowly. So the way we can now think of this convolution neural network is as follows. So we have the following architecture here as CNN. So we have an input layer, which we just leave unspecified here. So this could be an image of, let's say, 28 times 28 pixels with 3 colors. Just as an example here, this could be 28 times 28 times 3. And then what we have is a convolutional layer. And this is something which we can repeat many times. So we have the convolution part itself. I'm just writing this as a conv. But normally, the whole thing here is actually called the convolution stage. But that has now a intermediate step, which is called a ReLU step. So we often use the ReLU activation function to process the information which comes from the convolution stage. And then we have a pooling stage, which I'm coming back to here. So let's just write this as a pooling. Sorry, the naming here goes a little bit wrong. And then what we would typically do now is to feed this one into a fully connected neural network. So this is an FFN, which you will also write as an FC for fully connected. And this is then fed to the final output. So what you have now as parameters, which you would train by backpropagation, are the following. So here we have a training of weights, or the filter parameters. And there are also biases here. The ReLU layer and the pooling layer have no parameters, no training parameters. And then we would have the parameters here and also in the output layer. So when we have set up this machinery, we have performed a scaling down of the image by the convolution stage. Now keep also in mind that we can repeat this convolution stage many times. So this is often done because we want to make sure that if we just reduce the image dramatically, we may lose too much information. So we reduce it slightly, and then we have a new convolution stage where we perform a new reduction. And often what happens then is that we make many replicas of the image. And then we continue with several convolutional stages, which are then fed into a final fully connected neural network. So we would then apply backpropagation to the training of the feed-forward neural network and backpropagation to the convolution stage. So this is the basic essence of a convolutional neural network. So if you now look at some examples here, what are the dimensionalities and how many parameters would we end up with? Let's look at an example here. So we could think of having as an input a 32 times 32 image with 3 color channels. Then we are going to have 10 filters. A 5 times 5. And then we are going to set up a stride equal to 1. In general, the formula which we are going to get will also include padding, but we are going now to put padding P in this example here, P equal to 0. So when we have no padding, each filter produces then an image with the following dimension. So this is going to have now, if we now think of the initial stage, so we start with a dimensionality which has W2 of weight, of width, and then an height H2 here. What we are going to get then when we have this specific filter, so what it does now is that we introduce a new set of parameters. So we have the following. So let's just set up here. So we have the image which we are going to set up are the following types. So we have width for W and height for H and D for depth. So in this specific case, I put this to 32 here, both of them. That's the input. So we get, for the filters, we are going to get parameters, W and H, and also a depth, which is the number of filters we are making. So the new hyperparameters. So these are hyperparameters. Are going to be given by the K number of filters we are going to have their spatial extent, and we are going to assume that these are given by square matrices. So that means that this W is equal H, and we just call this for F. Then we are going to have the stride in the multiplications, or in the way we set up the convolution. And then we need the amount of zero padding, which we call for P here. So that means that when we take a reduction of a specific size, so we have a reduction of the original data, which has a width 8W1 and a height H1. What we get then is the following. So we get a new width, which is given by the original width, minus F plus 2 times P divided by the padding plus 1. And then we have an H2 here, the new height, which is given by the original height minus F plus 2 times padding divided by the stride plus 1. And then the depth is simply given by the number of filters K. So that means that what I have then, if I think of this image, which was the originally given by 32 times 32 times 3. Now what I said is I have 10 filters, and each of them have a 5 times 5, so that is F. So what I get then is that this W2 here is going to be given by 32 minus 5 divided by 1, the stride, plus 1. And you will see that when you perform the multiplications. So this is now going to be given by 28 times 28. And I'm going now to have a color channel, which we need to include as well, which I have omitted here. And I'm also going to have 10 images of this. So we need also to include color channels. Include color channels. So the original case, now we started with 32 times 32. And I'm going to make these filters here. So when we now look at the number of parameters I get, so per filter, what I have is 5 times 5 times 3 plus 1 bias. And that gives me 76 parameters per filter. Then I'm making 10 replicas, 10 filters. So that leads to 760 parameters. So each filter has now a dimensionality of 5 times 5, plus the color channels, and plus a bias, which we add, and that gives in total 76 parameters. So the dimensionality of the image was then reduced, if we look at this case, to 28 times 28 plus 1 here. And that's the dimensionality which we end up with. So sorry, just a moment. No, sorry, I was a little bit rushed here. This is equal to 28. And that leads to 28 times 28. So that's the dimensionality of each image here. So the parameters we need to train are typically then set up by the dimensionality of the filter. We add a bias, and since we are producing 10 new images, we end up with a total of 760 parameters which we need to train. Then there are some common settings which many people use for these type of parameters. You will find them in many of the examples which we have. So you put f equal to 3, you have stride equal to 1, and padding equal to 1. We have an f equal to 5, and s equal to 1. So these are common choices which people end up using. And then we have f equal to 5, and s equal to 2. And this padding is normally chosen as the one which fits best. So we often see that whatever fits best. So when you train a convolutional neural network, what we often end up doing then is to set up different calculations with different strides and different paddings and different dimensionalities of the filter. So these become hyperparameters which define the architecture of the network. And when you have defined these hyperparameters, you run the training, you find the weights, you have the number of weights and biases, and then when you have that, you see what you get, and then you rerun with new architectures, and you go back and forth like this in order to see which is the case which gives the best result here. So with these parameters, we can then start thinking of setting up our own convolutional neural network. And one of the best ways to do that, and this is where we will end today, is to actually look at an example where we use TensorFlow. So let's go back a little bit here. So stop sharing. And this is roughly where we will stop. And then there we are. So when I run TensorFlow, what I normally like to do is actually to use Google's Colab. And what I've done here is simply to run that in, let me just reduce the dimensionality here a little bit. Take that one down. So let me try to bring this up here. So this is the MNIST data set. And the first thing is just to read in the data set as we did last week. So this is just a printout of some of the handwritten numbers. So this is a very low resolution. It's an 8 times 8. So when you use TensorFlow now, the thing which we need to import are the same things as which we discussed last week. So we need to import the data sets, layers, and models input. So Keras is an interface to TensorFlow as a library, which makes the coding a little bit easier and also easier to understand. So we have a sequential network. And we have going to have a dense network. We have to include the optimizers, the regularizers, And in our case, we are going to distinguish between different categories. So we do this plain X train, X test, and Y train and Y test as before. And this is how we would set up the network now. And this is set up here. So we would now define one convolutional layer. And we define the type of fields which we have. So this is a filter, which is a 3x3 filter. We give in the input shape, which is now this set of numbers. And then we have the activation function, the relo. We also have a regularization term. We have the pooling layer. And so this pooling layer means that what we are doing now is that we look at the output in blocks of 2 and 2, and we pick the largest number of a submatrix of dimensionality 2 by 2. Then we flatten the output from the convolutional stage and the pooling stage, and we flatten that one. That goes into a dense neural network where we have an activation function like the relo function. And then we have the final output layer, which is defined by the categories which we have. And in this case, we use the softmax function. And we use the standard gradient descent as an optimizer. And the learning rate is just this set of learning rates, which you have seen before. So this is the way you could use TensorFlow with Keras, which is an interface to TensorFlow, to set up a convolutional neural network. Then you can do the training. And what we have here is just simply running here. Actually, the training takes much more time, but the quality of the results is more or less like the one we found last time with just a simple neural network. And you can see now the training, we have cases for 8 and lambda where we have an accuracy of 1. And you will also see in the test case that we have a case where we have an accuracy of 99%, which is slightly better than a human, which is roughly 98%. So we get more or less the same result, which we had with a standard neural network with this data set, which in a certain sense means for that small data set, running with a neural network is equally good as running with a more complex method. But if your data set increases, you will see now that a standard neural network will actually not perform as well. And if you scroll down, you will find an example on the so-called CFA data, which is a set of images of cars and trucks and frogs and animals and et cetera, et cetera. So this contains something like 70,000 data sets. And next week, we are going to look at this example as well. And there is a nice thing when you now set up the convolutional neural network. You see in this case, we have a convolutional layer with a max pooling. We have a new convolutional layer and max pooling. So we actually perform this 3 times here. And then you get a model summary, which tells you about how many parameters you have. So the pooling layer has no parameters, and this is indicated here. And then you see the total number of parameters which you get here. So this is something on the order of 56,000 parameters, which we are going to use in the training. And we are going to bring up this case next week. And then we're also going to discuss how we can write our own code for convolutional neural network. But as I said, for project number 3, if you want to do this, we don't recommend to write your own code, but rather to use the functionality which TensorFlow gives you and PyTorch, if you prefer PyTorch. And that will allow you to test both neural networks, convolutional neural networks, and perhaps other methods for an image classification problem. And this is one of the tracks which many have chosen for project number 3. So you could actually take the cancer data, which we have been analyzing, and look at the cancer data with, let's say, convolutional neural networks, if you want to, or have some image classification case, which is widely popular. Okay, I'm going to stop here. Also, if you have questions about the project, feel free to ask. Let's just stop the recording here.